You're done. I'll take it. I see. Who in here is taking anatomy? Guess that you would have done that. Did you guess?
No.
You guessed this? Right. Good. Sure. Merci. Is everybody on? The hammer, the anvil, and the stirrup are all little tiny bones in your inner ear. So you didn't learn that in anatomy? Or did you have to learn like the scientific name? It's much more difficult than I thought it was. I thought that was a beginning. So, we're going to start something new today. It actually is going to build off doing powers of trig functions. This is a new technique that we're going to call integration by trig substitution. I abbreviated the word substitution. Trig subs. So trig subs are going to really rest on these three big identities that I wrote up there. Sine squared plus cosine. Well, sorry, 1 minus sine squared is cosine squared. 1 plus tangent squared, secant squared, secant squared minus 1 is tangent squared. Those are three biggies that we're going to use a lot with trig subs. All right, so let's look at this problem that we're just going to jump into it, okay? Why can't we do this with a U sub? What is that missing in order to do it with a U sub that would be nice and friendly? Well, or just a regular x. A 2x would be glorious, but even if it was a regular x sitting out here, we could do it. Okay. Integration by parts might be an option here, but honestly, that radical scares me with integration by parts. Does it scare you with integration by parts? I mean, anti-differentiating stuff with radicals and differentiating stuff with radicals, this gets pretty ugly, pretty fast. But if you notice there, inside that radical, you have something that looks like a perfect square minus x squared. Does everybody see that? You have a perfect square minus x squared. Okay? So I'm going to make this substitution. And you'll see why in a second. I'm going to say, let's let x equal 4 sine theta. You might be like, why the flippity flip did you do that? Okay. Well, just hold on. Since I'm saying x is 4 sine theta, can you go ahead and tell me what dx would have to be then? Because, you know, it's just like a u sub, everybody's got to come out. So that's going to be 4 cosine theta. Okay? So now if I make this substitution, I get the square root of 16 minus 4 sine theta squared. And then, I missed the d theta here. Did you guys forget that too? 16 minus 4 sine theta squared. And then over here, I'm going to put 4 cosine theta d theta. And now if I do a little bit of cleaning, what's 4 sine theta squared? Isn't that 16 sine squared? Isn't that the same thing? Because you have to square both of those, the sine and the 4. Times 4 cosine theta d theta. And right here, I can factor out a 16. You see that? Now I have the square root of 16 times all that other stuff. And I can actually break that square root up into 2 separate things because they're being multiplied. So this is the square root of 16 times the square root of 1 minus sine squared times 4 cosine theta d theta. But what's the square root of 16? 4. And what's 1 minus sine squared? Cosine squared, right? And what's the square root of cosine squared? Cosine. So this ends up being 4 cosine theta times 4 cosine theta d theta, which means it ends up being 16 cosine squared d theta. Hey, we know how to find the antiderivative of cosine squared. Maybe we memorized it for this morning. Megan, what is it? I know you know. 1/2. So I'm going to pull that 16. Whoops, I don't mean. So what is it?
1/2 x plus cosine x minus.
So instead of x, though, here, what are we going to have? Because this is the antiderivative of cosine squared of theta, right? So we'll have a theta here plus, and then what did you say? Sine theta, cosine theta? Okay. So I guess if I do some simplifying here, that ends up being 8, right? So is that our answer? Are we done? We got to go back to x. And we got to add some chips, I guess. So how do we go back to x? Okay. Well, right here, this was our defining moment in this problem. Literally, the defining moment of the problem. Okay? X equals 4 sine theta, which means that x over 4 equals sine theta. Agreed? So over here, Where it says sine theta, I could put x over 4. But I need theta, and I also need cosine theta. How am I going to get theta and cosine theta from this sort of defining equation? We're going to draw a picture. Can you draw this situation here? Can you draw me a situation where sine of theta is x over 4? If I call this theta, hello, x over 4, opposite over hypotenuse. Which makes this side of the triangle what? Or that leg, I should say. 16 minus x squared, square rooted. Does that radical look familiar? That's the radical that was in the problem. That's almost always going to happen in this, by the way. Okay. So what's theta? Well, theta, we could say, is the inverse sine of x over 4. So I'm going to go over here and say theta is the inverse sine of x over 4 plus sine theta, x over 4, times cosine theta. What's cosine of theta? How do you get that? Look at the triangle. And you use SOHCAHTOA. What's the cosine of theta? Adjacent over hypotenuse. Plus chips. Now, does that simplify? Sure, you can make that a 16 if you want. You leave it like this, I'm probably fine with that too. Holy cow, this is a hot mess, isn't it? I mean, look at that answer compared to the problem. Way more complicated. Right? Question?
So we found theta equals sine or inverse sine of x over 4. Can you just plug that into all the thetas? Because that would cancel out the sine and you just get x over 4. And if you plug it into cosine, would it equal the radical?
So cosine of the inverse sine of x over 4 equals that. Yeah. But I want you to write it like this. Yeah. Because I want to see that you understand that triangle thing. Now, Mr. Critch is actually teaching this right now. I walked past his room and I heard him teaching just that. Drawing those triangles and inverse sine, cosine. But hey, we're going to be doing that tomorrow. How about that? Okay, so how do we like that? A lot of steps here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 step problem. And then this is a whole nother, crazy stuff. Yeah.
How did you get inverse sine x over 4 equal theta?
How did I get inverse sine of x over 4?
Yeah.
Well, it started with this, okay? Now, you might be wondering, like, how did you know to do that? Well, I'm going to tell you, okay? So it started with this. And then I said, well, if that's true, then this is true. And if this is true, then that's true. Right? So how did I get x equals 4 sine theta? How did I get that? It goes back to this identity right here. I strategically picked that because it looked like something squared minus x squared. Do you see that right here? 1 minus sine squared was cosine squared. We ended up getting eventually here a 1 minus sine squared. You see that? So the rule is this. Okay, I guess I'll write it right here. If you have a radical that involves a squared minus x squared, you let x equal a sine theta. And then dx will be a cosine theta. Okay? That's the substitution that you make. Then you turn it into a big trig problem. All right?
It's always sine.
Yes. You could use cosine, but then you got to deal with the negative. So it's easier if you just use sine. Right? Because you could flip-flop this. Becca, like you could be like, oh, x equal a cosine, and then dx is a sine, but it would be negative. And now you got to keep track of that negative the whole problem, which is nobody wants to do that. Okay, let's try another one. Let's try one with a different substitution. Lots of work involved in trig subs. But they have a little bit of a feel of like proving identities. Remember identity proofs? That's how these kind of feel when you do them. You just like get all warm and fuzzy. Like, and you know you did it right when you finish it. Like you just know. How about this one? Let's go. The square root of. Well, let's do the same, almost the same problem, but it's going to be very different. 16 plus x squared. Very similar, right? Very similar. But it's going to be very different. Okay? Now, if you understood why I made the last substitution what I made it, you might be able to look up there and tell me which substitution we're going to make here. How is this inside that radical, how is this one different than the last one? It's plus x squared. This one is of the form a squared plus x squared. Which one of these three identities do you think we're going to make use of? The second one. So what do you think my substitution is going to be? Let x equal 4 tangent theta. And then what's dx going to be? 4 secant squared theta d theta. So now when I sub in, I'm going to have square root of 16 plus 4 tangent squared theta. Dx is 4 secant squared theta. So this is going to be 16 plus 16 tangent squared theta times 4 secant squared theta. So that's 16 times 1 plus tangent squared theta times 4 secant squared theta. So how is that inside the radical? What's that going to simplify to, basically?
You can do to theta. 16 times.
Well, the 16, we're going to radical that and get 4. 1 plus tangent squared is secant squared, and we'll radical that and get secant. So this piece right here is going to simplify to 4 secant theta times 4 secant squared theta.
Can I have the quiz back? I'm so close to getting the last one right.
So now that's 16 secant cubed theta. Oh, shoot. Now we have to integrate secant cubed.
Oh, it's 1/2.
Hmm. Abdel memorized it?
No.
Oh, who's saying it? Oh, Abdel was looking my direction and I heard voices, so.
It's 1/2 secant x tangent of x, and then minus 1/2 the natural log of secant of x plus tangent of x. And I noticed that the first one is the derivative and the second one is the antiderivative.
Yeah. So rather than like going back and working that out again, we're just going to pull that out from somewhere that we've done it before. And we saved a little bit of time there. Okay? Are you sure this is minus?
No,
I think it's plus. My first year teaching this class, 23 years ago, this girl right here, Caroline Jackson, I remember she had the antiderivatives of secant cubed and secant to the fifth memorized. So anytime they would come up in class, it would be her that would say, oh, 1/2 secant to the, like, for some reason, I don't know, she just memorized those. The cubed and the fifth. Like, the cubed is just this with another term out on it. But we're not done here, right? What do we have to do? Oh, crap. We have to go back to this defining equation and draw a triangle. So if x equals 4 tangent theta, then x over 4 equals tangent theta. Can we draw that triangle? Can we draw theta whose tangent is x over 4? Which makes this hypotenuse what? Square root of 16 plus x squared. Look at that. That radical popped back up again. That's going to happen almost every single time. Okay? All right, what do we do now? Okay, so let's just take the 1/2 out and call that 8. So what's the secant of theta? Look at the triangle and tell me what the secant of theta is. It's 1 over the cosine of theta. Or it's the reciprocal of the cosine of theta. Yeah. And tangent theta we already know. Oh, we already did the 1/2, sorry. Oh, and I just used that again. Secant theta. Plus tangent theta. Whoops, forgot in this and then put the brackets. What are we missing? Chips? Now, crazy enough, if we did this problem for homework, you would feel all warm and fuzzy inside after getting to this point, and then you would probably look in the back of the book. And that's not the answer in the back. Okay, and don't get discouraged when that happens, because we're going to do some simplifying here. Watch this. This 4 right here and that 8 is going to become a 2, right? So that's going to be 2 square root of, or 2x square root of 16 plus x squared. You cool on that? Plus 8 natural log of radical 16 plus x squared plus x over 4. You cool with that? And then there's this property of logarithms that says, hey, this log of a quotient is actually the same thing as the difference of the logs. And if you look real carefully, this right here, When I multiply it by 8, that's a constant. So it's going to get thrown into the chips. Oh, it is plus X. Thank you. Sorry about that. But this is going to get thrown into the bag of chips. So the answer that you're going to see in the back of the book is this. Okay. Now, if you have to do that, no, I'm happy if you leave it like this or like either one of these. Okay. But you got to know that that's out there. So let's quickly summarize this. We have this rule here. What's our rule? If we have a squared plus x squared, then x equals what? A tangent. Okay? Dx is going to be a secant squared. What's the last one, do you think? If you look up here. If it's x squared minus a squared. A secant. Okay? So I'll put some problems on Google Classroom for you to try tonight. I'm going to try to keep them the ones that with just those first two substitutions. Because I wasn't sure how many of those we were going to get through. So this is so fun. Yeah.
You draw the triangle, like with like original triangle. No, like the one like is it like X 3 radical 2? Like I don't know the original triangle. Like how I don't know.
It's organized, like
Yeah, how it's
what
organized.
each side is related to the other side, like how, like if you have to multiply.
Like the original.
I don't know what you mean by it. It's so controlled.
Oh.
No, I guess
You're thinking of 30, 60, 90 triangles, which has nothing to do with that.
I don't.
No, he means like,
I have
how
no
do you
idea.
get like this from like
Yeah,
base
from
to
that.
How do I get this from x over 4 equaling tangent theta? I put theta in the corner and
No, I get that.
These two, I'm getting it. Yeah.
Pythagorean theorem. Is that what you mean?
I just isn't it like one is like X,
4 squared plus x squared equals
that's what I do.
I think you're confusing 30, 60, 90 and this. This is just SOHCAHTOA. So if you write this,
Alright, I get that. I can do that.
okay, so we got that. So put theta in the corner, okay? And make theta have a tangent of x over 4. Opposite over adjacent. How do I get this side as the Pythagorean theorem?
Oh.
Tuesday,
Oh, yeah.
got messed up.
Yeah.
Friday during 6 months on.
Yeah, yeah. I
Friday,
forgot all about that. Oh, yeah.
Yeah, because Tuesday.
Yeah, yeah. Oh.
It's on Friday, 6 months.
Friday, yeah. Friday.
Yeah, I looked on the weather. We're not going to have school on Friday.
Yeah.
Sounds good.
Wow, you're looking memorized all the day. I'll do it later. My stats test got pushed back. Carrie, you would-
Oh, Carrie, thanks.
You know, I would love for the math test to be pushed back.
Well, it wasn't actually supposed to
What
be.
math test?
It's a quiz.
Oh my God.
It's the same thing.
I said I was.
Where do you get your math? I fly somewhere. It doesn't look like that's from an airline.
I have no idea.
They're just sitting there.
And when I saw you driving home from practice yesterday, who were you with?
My dad. That was so awesome.
Is your dad retired?
No,
His license plate
That's
says
just the
retired.
license plate. Like can deal with people's retirement. It's like a financial.
Oh, okay, gotcha.
Yeah, I was a little confused.
Anybody else?
I looked over and I was like, oh, that's Billy.
Yeah, and then we just kind of stared at each other. Their other license plate was baby chicken.
Do you want to? How do you do it?
This is not gonna go well.
How am I doing today? I'm doing great. I thought you weren't going to be here today.
No, I told them Friday I was gonna come take the quiz.
Oh, you're like, oh, calculus is too important than just standing around in Trin Arena.
Yeah. There's so many people we just get even doing.
Yeah, you guys. I mean, there's a lot of you, a lot of standing around. You don't have to work too hard. And it's even going to be less today because there's going to be so many fewer people. So many people got their shot yesterday.
So I literally sat in like the conference room in the back and was studying.
That's beautiful. Oh, baby.
Gary, do you work tonight? Yes, I do. Like that for you? Like I have a note, like that with like the notebook or whatever. I just pulled up straight. You know, like the important idea thoughts.
Yeah.
Really? We probably should have studied.
Wait, this test is gonna be Tuesday?
No,
Oh.
not test.
I'm thinking about a test for this class.
No.
So it's sinus to X equals 2 sinus cosine. And then cosine to X equals cosine.
This is the most scared you've ever been for a quiz.
Yeah.
Really?
Two cosine to X equals 1. And then 1 plus the squared X equals 2. I'm proud of you. That was hard.
How many thumbs are there on
Three?
there? Three of Bill lied to us. Said yesterday, he said it was two.
Well, I might have said two. I might have said 2 or 3. I don't know. Let's just get started. I mean, we're all here. We're just sitting around doing nothing. KD, what's happening?
Nothing.
Huh? Whoop. Oh, look at that. How it rolled, slid down your back, right into his hands.
Yep.
Glorious.
Are you gonna give us a bonus point?
Oh, yeah, baby. So the last period's bonus question was rather difficult. I'm going to give you a different version of their question. In what, or let's see, where in your body would you find your stirrup?
Your what?
Stirrup. Stirrup. Where in your body would you find the stirrup?
Inside my body?
That doesn't count. Is anybody watching us live right now? Not right now. Everyone say hi to Jack McAfee. We're taking our quiz, Jack, so just hang out. Just hang loose, bud. Shit, that's when you cut bait. If you're done, I'll take it. You gotta hold on. Oh, that worked, doesn't it?
No, it's in patient form. It's okay. I've accepted it.
Are you done? Would anybody like this Coca-Cola? It is actually, that's what it was originally made for. Coca-Cola was originally made as a headache.
I didn't know like actual cocaine.
I think that might be a little bit of a stretch, but there was some sort of connection to the cocoa plant. That we did with cocaine comes from. I mean, cocaine and chocolate come from the same place. I believe. I think chocolate comes from the bean. Maybe.
The cocoa.
But where does cocaine come from?
I have no idea.
It's a different plant?
I can tell you what opium I do have menthol and shit
It's not the cocoa plant?
like this. It's like the chocolate one and COCOA. Pretty sure. Are you looking up where cocaine comes from?
What is cocaine? Coke, snow, powder, blow. Cocoa leaves. Coca leaves, sorry. Excuse me, coca leaves. Which is not to be confused with cocoa. The coca plant, not cocoa.
So different.
Yeah, they're different.
Actually, I think it's material science. His hands.
It's coca and cocoa. But Coca-Cola did have that.
When it was originally came out, cocaine was under Eagle. Yeah.
In the early 1900s, purified cocaine was the main active ingredient in many tonics and elixirs developed. It was even an ingredient in the early formulations of Coca-Cola. There you have it. No. You can have this. I'm really junk fooding you up today. Coca-Cola and Reese's. I mean, that couldn't get much more healthy than that.
I work for number 3.
Oh.
So I just simplify it and
All right, well, that was fun. Your stirrup. The hammer, the anvil, and the stirrup are 3 bones. They're the smallest bones in your body. They're in your inner ear.
I did ankle.
A lot of you put ankle because it sounds like, or, stirrup, like it's connected, Well, I was confusing last period because I asked them where you find your anvil. And a lot of them said your ankle because it sounds like anvil. Hammer, anvil, stirrup. They're little bones in your inner ear.
I didn't even know that yours had bones.
What?
I didn't even know that yours had bones.
Inside, like way in there.
Are the parts, like the things that go on the horse, named after the bones, or the bones named after the horse?
I think it's the bones are named after that. Because they look like a hammer, an anvil, and a stirrup.
Yeah, I actually agree with you about that. You've got like number of bones in bodies, and they're actually debated whether that counts as this. Like,
1 or 3?
It's actually debated whether it counts them all in your bone count.
Oh, because they're cartilage?
No, I think they actually are bones. There's still a lot of debate on what to consider bones.
Oh.
The 206 number is just kind of like pulled out of thin air. There's actually no real evidence for that number. It's around the correct number, but couldn't you just count them? No. No, that's why the problem. It's really hard to count.
All right, friends.
We'll just wait for someone to die.
Just slice them up.
You go from like
It's something that has extra.
Get counting.
400 to 190.
So we're going to start our next technique of integration, our next anti-differentiation technique. We call it integration by trig. Well, if we want to use the full word, we say integration by trigonometric substitution. It's easier just to call them trig subs. These kinds of problems are very similar to the ones that we have just finished up and we just took a quiz on, in that they involve making use of some trig identities. And most notably, the trig identities that are going to come into play the most are these 3 right here. 1 minus sine squared, cosine squared, 1 plus tangent squared, secant squared, and secant squared minus 1, tangent squared. Okay? So those are the 3 identities that we're going to make the most use of in trig subs. All right? So let's jump in and do a problem that involves a trig sub so you can see how this kind of works. So I'm going to, oopsies. So if I were to give you that problem on your last quiz or, weeks ago, that would have been a really mean thing to do because you wouldn't have known how to do it. That problem cannot be done with a U sub. Why? What's it missing in order to make it a very easy U sub? Another X. It would be glorious if it had a 2x, like right here. But even if it just had an x, we could do it. But it doesn't have that. So then I look, okay, could I do this by parts? Well, maybe. But if my choices for parts are not that great. The only choice I have really is, I don't have like the radical involved, and I don't really want to get involved with a radical. Right? I mean, radicals are nasty. You think about the derivative of a radical, what happens? You get another radical, but it's in the denominator. Like, yeah. That's heinous. Okay? So, sort of the next thing that we're going to do here is say, all right, well, when radicals are involved, and we've got like, do you see that that's something squared? Like a perfect square minus x squared? You see that? When you have that, and you can't do a u sub, then a trig sub is sort of your next go-to. All right? Now, I'm going to tell you right now, we're going to make this substitution. And you'll see why in a minute. But I'm going to let's just say right now, we're going to say let x equal 4 sine theta. Now, you might think I just pulled that out of the sky. And it certainly looks like I did. But there was some major strategy in why I chose that. And you'll see why in a second. Sammy, which question?
It doesn't it not do a perfect square?
What?
Doesn't it not be a perfect square?
Anything is a perfect square.
Oh, yeah.
I mean, 7 is a perfect square. It's radical 7 squared. I mean, think about it. Right? I mean, isn't 7 a perfect square? Well, sure it is. It's radical 7 squared.
It doesn't hold a formal definition, though.
Yeah.
I think
I mean, it doesn't. I mean, it's saying it has to be a square of an integer. But all right. So I'm going to make this substitution: x equals 4 sine theta. All right, just like we did before when we made substitutions. Let's tell me what dx is. 4 cosine theta, d theta. Does that sound good to you? Okay, so this is a substitution. So it's just like u subs. All the x's are going out and betas are going in, I guess. So this will be the square root of 16 minus 4 sine theta squared. And then dx is going to get replaced with 4 cosine theta d theta. All right, so now I guess I'll do some cleanup here. What's 4 sine theta, all of that squared? What does this become right here when I square that? 16 sine squared, right? The squeaking is starting to drive me nuts. Is it starting to drive you nuts? Well, I need something that's going to show up on the screen for these people right here. Can I factor out a 16 there? No, I can't do whatever I want. Okay, so now what? I have 16 times this, and it's all radicalized. I can think of that as radical 16 times radical 1 minus sine squared times 4 cosine theta d theta. Now I'm going to go up top here. Radical 16 is also known as 4. 1 minus sine squared is also known as cosine squared. And since it's radicalized, what's the square root of cosine squared? Just cosine. And then I've got this 4 cosine. So this ends up being 16 cosine squared d theta. So do Do we know the antiderivative of 16 cosine squared? How many of us memorized the antiderivative of cosine squared for today's quiz? Well, we should have probably. You can take that 16 out first. Nah, you stupid idiot. Cosine squared d theta. So what is the antiderivative of cosine squared? 1/2 times x plus sine x cosine x, right? But since this is theta, it's going to be theta plus sine theta cosine. And you guys want to go ahead and marry the 16 and the 1/2? Call those 8. So are we finished? What do you think, Samuel? Yeah, we got to put this back in terms of x.
Yeah.
We have an answer that's in terms of theta. But we need to put it back in terms of x. So with this problem, this right here was sort of the defining moment, literally. X equals 4 sine theta. Since that's true, that's true. Agreed? So in our answer over there, where you see sine of theta, you can substitute in x over 4. But you got a lot more stuff over there than just sine theta, don't you? You got a theta and you also got a cosine theta. So it looks like we're going to have to take this right here and tell this story another way. How do we tell that story? With a triangle. Draw a triangle and call this angle right here theta. Hi, theta. Now make this right here be true in this triangle. The sine of theta has to equal x over 4. SOHCAHTOA, opposite hypotenuse. Which means this other side right here, because of the Pythagorean theorem, is equal to what? Square root of 4 squared minus x squared. Hey, does that look familiar? That radical? Have I seen that radical somewhere before? Oh yeah, it's the problem. Okay? So one thing that you got to understand here, friends, everybody look here. This defining equation, this, and this, all three of these are pieces of information that are telling the same story different ways. Right? If x equals 4 sine theta, then this triangle has to be true. Right? So now, let's go back over here. Can we use that triangle to fill in the pieces over here? Well, what's theta? You can name theta lots of things.
Arc sine of x over 4.
Inverse sine of x over 4. You could name an inverse tangent of x over radical 16 minus x squared if you wanted to, but you might as well just stick with the one you started with. So if you want, I can write over here too, theta equals inverse sine of x over 4. Like that's another piece of this little puzzle here. Right? They're all the same. All of those statements are just other ways of, or different ways of telling the same story. So theta is the inverse sine of x over 4 plus sine theta, we already know is x over 4, cosine theta. Can you tell me what cosine of theta is from that picture? What is it, Mia? Now, could you marry these and make that a 16? Sure. Or you could just leave it like that. Now look at that answer, people. It's hideous. Middle school yearbook ugly. That's what that is. Right? I mean, awful. And all that work just to find this little antiderivative. Plus chips, oh yeah. So now let's go back to, where did I get x equals 4 sine theta? Did I just pull that out of thin air? No. I got that. I chose that because I knew this was going to happen right here. This is what I wanted to happen. That 1 minus sine squared to become cosine squared. And then I was going to square root it. Because I ended up making use of this identity right here. So let's sort of make a statement, make a rule. If we have something of this form, a squared minus x squared, then x is going to equal a sine theta. And dx is going to equal a cosine theta d theta. Yeah. What? Does it have to be the square root? Not necessarily.
A root of it, because if it was just like normal.
It could be any root of it, or it could just be just normal too.
But like if it was normal, wouldn't it be easier to do like the normal?
Possibly, unless maybe it was something like this. That might, I mean, that, then it's not just so easy.
So it's the power or something.
But that's not to the power.
The power of my.
Okay. Yeah. Or this. Well, then it's inside of a wrap. Yeah. That sounds good.
So they got
That was fun, wasn't it?
No.
No? I love trig subs. Let's do another one. For some reason, we got through this next one in last period, which we're not going to get through in here. I don't know. Did you guys take longer on your quiz? I should have taken it from you. Almost the exact same problem, but not. This is 16 plus x squared inside of a radical. And I'm going to make this substitution. X equals 4 tangent theta. What's dx then? 4 secant squared theta. So this ends up being the square root of 16 plus 16 tangent squared theta. I'm doing that in my head there, that's squaring, times 4 secant squared theta. Now, if I factor out that 16, look at that. Forgot d theta here. And now this ends up being 4 times the square root of 1 plus tangent squared. Times 4 secant squared. So how is this going to, what's this going to turn into? 1 plus tangent squared is secant squared. The square root of that is secant. So this ends up being 4 secant theta times 4 secant squared theta, which ends up being 16 secant cubed theta. D theta. Oh, shoot. Did anybody memorize the antiderivative of secant cubed? Someone in last period did. They just whipped it off like, it's like, whoa, impressive. Okay. I'm going to tell you what it is because I know it. It's 1/2 secant theta tangent theta plus 1/2 natural log of secant theta plus tangent theta. That's the antiderivative of secant cubed.
Yeah, why are there two d thetas?
Because I'm an idiot. Yeah. So now what I need you guys to do, because we're going to write, I mean, we have to go back to this. That's theta. Make this defining equation and give me the triangle. X over 4 equals tangent theta. So this is x, that's 4. What's the hypotenuse? The square root of 16 plus x squared. There's that radical that was the problem. So now you guys can take this and go to this and finish this out. Now the video, you can watch the video. I did that last period if you want to check your answer. So we have some problems to get us started in Google Classroom for this fun stuff. Trig subs, you guys can come in. I mean, it's not. We're just learning trig subs here.
Oh, that's wrong.
I don't even think I know those.
I now never learn. I hate it.
Have a great day. How many of you are going to lunch right now?
I'm not.
You want to where? You just have.
Actually, yeah. I should probably take one because all the way across the school.
I dropped it.
I don't want to finish for it.
I would have been.
Oh, okay.
I know. Have fun.
I took Spanish for 11 years and retained none of it.
11 years.
11 years.
You should be disappointed in yourself.
Oh, no.
I don't know how many I have.
We never
But check on Google, their classroom. There's the problems are out there. So fun. Oh, I gotta end this stream. See you later.
Make my face the thumbnail.
It's already too late.
Yeah, the thumbnail's already happened.
Oh, great.
I went from.
Yeah, you went to the